that you would not get in the video. And that's how we won Vietnam. We didn't win Vietnam. It was not how that happened. Part 3, a deeper understanding. Superman Returns. All right, so bias and variance are old two friends. Can someone remind me, what is bias and variance again? See, the eyes are rolling. It's a good sign. What is bias and variance? Give me some kind of even a crude description of bias or variance.
Variance is error.
Variance is error. Now, I would generally consider bias to be the error. Bias generally quantifies the actual error in your model. So let me ask you in a different way. If I told you a model generally had a low bias, what would that mean to you? What does a low bias model generally mean? Tell me, what is it?
It's more right.
It's more right. Yes, honestly, it is on average correct at predicting the thing that we're trying to predict. If I try to fit a crazy 8-degree polynomial to some data, yeah, it'll be right a lot of the time. Now, if I tell you the model had high bias, what does that mean? A high bias. Less accurate. What about a low variance? What is a model with low variance? Pay no attention to the man behind.
The results are less staggered.
The results are less staggered. Yes, you're on the right track. The results of what?
Of certain predictions.
So the model, exactly. So the results of your predictions, i.e. otherwise called the model tends to be fairly consistent as you change the sample of your population. Yes?
Can you put that to a confidence interval and margin of error?
Is that an answer?
Can you put that to a confidence interval and margin of error?
Yes. You can absolutely equate that to a confidence interval, which is down here. Absolutely. In fact, yes, good. Our confidence interval, which we'll get to very shortly, is exactly earlier in class when I said we're going to be talking. Sometimes it's hard to say, we expect it will be this point exactly, this many in sales. It's easier sometimes to say, we believe it's going to be within this and this range. So in the beginning of the class, when I showed you the TV versus sales, and I asked you, if we spend zero money on TV, how much would you expect to sell? You said between 5 or between 2 and 5. That's an interval, which we'll very clearly define as a confidence interval. So if a model has a low variance, that means that as you change your underlying population sample, which we do during cross-validation, the train test split, as you change your random sample, your model stays very consistent. Whether it's consistently high or low bias is irrelevant, but it's consistent. Now, if a model had a high variance, it means the opposite. Even if I slightly change the training set, my model might be wildly different. So if you recall those 8-degree polynomials from the previous class, an 8-degree polynomial will change drastically based on the number of the different points that I tell it to train to. So linear regression is a low variance, high bias model. Under repeated sampling of underlying population, the line will stay roughly in the same place. So lines aren't very prone to wildly changing. It's high bias because it rarely fits the data well, which sounds bad when you say it out loud like that. But a high bias does mean that the line will rarely fit the data well. So usually, when people turn to a linear regression, they are usually trying to find correlation relationships between variables. They're not always trying to find a very accurate prediction. Sometimes they just want to understand how the predictors relate to the response. And then they might choose to do a more complex model with a lower bias later on. So linear regression provides a very simple way of understanding how coefficients relate to each other. And we'll see exactly how in numbers. Now, confidence intervals. So stats models calculates 95% confidence intervals for our model coefficients, which are, you can interpret in the following way. Confidence intervals can be tricky because it's really easy to say it incorrectly. So if the population from which the sample was drawn was sampled 100 times. So, out of the 200, if I randomly take a portion of that 100 times, whether it's 10, 15, 20%, if I randomly take 20 points out of 200 100 times, 95 of those confidence intervals would contain the true coefficient. So, let me actually draw that out. Let's say on trial 1, I pick 20 points. And again, let's assume that we're doing TV to sales right now. Let's say I pick 20 points, TV and sales. Now, of those 20 points, I calculate that the coefficient, our beta 1, our coefficient for TV is inside of the range, what was it, 0.04 and 0.06. Somewhere in there. Our 95% confidence interval is in this interval. Now, what that means is, if I took several trials, trial 100, each trial, I'll take 20 points, and I'll say, okay, of these points, it seems like it's kind of between 0.045 and 0.065. It's in that range. If I keep doing this and creating different intervals, I'll end up creating 100 intervals. Of those 100, to the video people, I just blanked. But really what happened was crazy people are outside. Of those 100 intervals, 95 of them will contain the true value of the coefficient. What the confidence interval is not is the following. What it's not is, well, it's very tempting to say, well, we have this one interval and we're 95% sure it's in this interval. While that sounds a lot cleaner, that's not exactly what the confidence interval means. It just means that if we randomly took points 100 times, and we did the calculation to find our 95% confidence interval, what is that calculation? There's a textbook out there that tells you the calculation using the standard normal population, z-score, blah, 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 blah. If you are very interested in learning the formula, which I will not do in class, please feel free to find any one of us and we'll happily explain to you the formula. But trust me when I say, every time you take a random sample, it will calculate a range of values for your coefficient. If you do that 100 times, 95 of those will have the true value of the coefficient inside of it. That's what the confidence interval means. Let's see when we create it. Now, before we created our LM, our linear model, and if we do our conf_int function, it will actually show us the confidence interval of each of our variables. So in this line, our intercept, our 95% confidence interval, is 6.1 and 7.9. Our TV coefficient is 0.042, 0.0528. At this point, it is incorrect to say, I am 95% sure that the actual TV coefficient is in this range. That is an incorrect statement, unfortunately. That's not what the 95% confidence interval means. Sorry, I wish it were. That's a lot easier to say, but that's not what that is. Do you have anything else? Do you have an easier way of explaining?
Not really.
Fair enough. Fair enough.
Are people understanding so far? Or?
I want to explain a little bit more, just in case. The reason we can't say that is the following. This is only a single sample of the data, not the entire population. So as we take samples of the population, we can generate this interval. Now here's the problem. We only have data for 200 markets. there are a lot more people, hypothetically in this situation, there are more than 200 markets selling this product, have their own budgets. It's like in the World Health Organization of the drinks data, we didn't have every single country in there. We just didn't have it. We're pretty much always at a disadvantage when we don't have the entire population's data. Why do I keep saying population, and what does that mean? A population is the entirety of the subjects that you care about. So if I'm trying to look at, or how about this? If I'm trying to understand, if I want to know the average height of a woman in the world, I will have a very, very hard, near impossible time getting the average height of every single woman in the world. By sheer fact of, by the time I'm done, women will have died and been born. I just can't do it. It is physically nearly impossible for me to find the height of every single woman. So what do? The census, will take a sample of women, find their average height, and then use that to estimate the height of all women. That's how statistic was born. In fact, the word statistic literally means a characterizing element of a sample of your population. That's what a statistic actually means, correct? Yeah, okay. Because if you are able to do it for the entire population, it's no longer called a statistic, it's called a parameter. Terminology. That's what I learned at least. I'm pretty sure that's what videos and class taught me. Hopefully they're correct. So statistics literally is a study of samples of population. 200 markets is a sample of our population. This is merely one sample of all of our population. It's not all of it. So this is not enough to say we're 95% sure it's going to be within this confidence interval. The true coefficient is either in this interval, but it might not be. We can't actually know unless we take 99 more samples of that data. We can estimate the coefficient with the data we do have, and there will be uncertainty about what it actually is, but it's better than nothing. We can take this interval and say, okay, it will likely, very likely be in this range, but we can't say for sure that it will be in this range. I linked to an article here that explains confidence intervals, again, if you want to go back and look at it. Now, the 95% confidence interval is just a convention. You can create 90% confidence intervals. You can create 99% confidence intervals. If I remember correctly, the Board of Psychology, whatever national thing, their standard is 95%, if I'm not mistaken. So if you ever read a psychology paper, they're usually using 95% confidence intervals, usually. But you can change it. In fact, there's a problem that if you lower your confidence interval, you are more likely to have your data fit to what you wanted it to be. Because inherently, it kind of makes sense. If you lower that number, you only need less of those intervals to match what you want. So if you could have a 50% confidence interval and only half of your samples, you only need half of your samples. So that's why they have to make a standard of 95%, because if you go any lower, it's getting a little iffy about how good your results are. Yes?
Does confidence intervals only apply to continuous data sets?
Yes.
So it's like a yes or no?
Yeah. So what you could do, good question. So the question is, is a confidence interval only for continuous variables? Could it be for yes and no? No, unless you define yes and no as being a probability between 0 and 1. So you can say the probability of it being yes is between 0 and 1. Now that can be a confidence interval. You could say it's between 0.9 or 0.56 and 0.78. It's a probability. But so you can turn a true or false into a continuous variable by making it a probability between 0 and 1. And actually, you're kind of getting into what we're going to be doing on Wednesday called logistic regression. So that's a very good question. So no, short answer is no, you can't fit a confidence interval to a categorical. But if you rephrase the question as not yes and no, but probability of yes, you can create a continuous variable. confidence interval out of that variable. So the 95% confidence interval is a convention. It truly is. But I prefer another route called hypothesis testing. Now, if you've taken a stats class in high school or college, you might have remembered terms like chi-squared, or t-tests, or z-tests. And then right now you're probably shrinking back into your shell because that was not your favorite part of class. But that's fine, because I'm going to explain p-values again, and we have a doctor in statistics. Is there a doctor in the house? Yes, there's two, actually. There's doctors in the house, so we're fine. So, hypothesis testing. Here's the general gist of hypothesis testing. Very general gist. You have a null hypothesis and an alternative hypothesis. That is the opposite of the null. This is just terminology. Null hypothesis, the alternative hypothesis. Now, you check whether the data supports, this is kind of where it gets weird terminology, supports rejecting the null hypothesis. In other words, you're rejecting the null hypothesis. Or you fail to reject the null hypothesis. The terminology is weird, but it really matters. It's really specific for a really good reason. I'll say it again. The data either supports rejecting the null or fails to reject the null. Note the phrasing of failing to reject the null. It's not saying that the null is correct. It just means that the data fails to reject it. I'm not saying it's right, I can't reject it. I have nothing else to say, I can't reject it. It's a difference in terminology, it's a subtle difference in terminology, it's very important in terminology. And we'll see it happen. So, for our model coefficients, here's how we can use hypothesis testing. The null hypothesis is that there is no relationship between TV and sales. There's no relationship. If there were no relationship, beta 1 would be 0. That's our null. Our null hypothesis is there's no relationship. So we're going to either support rejecting it, so we're either going to reject the null hypothesis and the alternative being there is a relationship between TV and sales, or we'll fail to reject it. It doesn't mean there's no correlation, it just means that the data doesn't support rejecting it. Maybe if you got more, it might reject it, but as it stands, the data does not support rejecting the null hypothesis. I'm sorry, I'm kind of beating a dead horse, but that terminology is very, very important. So the null is there's no relationship. The alternative is there is a relationship. Not saying positive, negative, or anything else. There is some kind of a relationship, which means that beta 1 is not 0. Beta 1 actually is a number that's not 0, and sales will move along with TV advertising budget. How do we test it? The p-value. Now, p-value you've probably heard around in stats class and in other classes around. Here's what it means. Here's a one-liner, and I think it kind of sums it up nicely. The p-value is the probability, so it's 0 and 1, probability that the relationship that we're observing is occurring purely by chance. It's the probability that what we just saw was random coincidence. So, if the p-value is less than 0.05, if we're at a 95% confidence, so 95.95, if the p-value is less than 0.05, and again, p-value is the probability that what we're looking at was purely by chance. So if p is less than 0.05, what does that mean? Does that mean it was very likely to chance? No. Very unlikely that what we just saw happened purely by coincidence. If p is less than 0.05, we will get to reject the null in favor of the alternative. If p is less than 0.05, we will reject the null, that there's no relationship, and accept the alternative, that there is a relationship. Essentially, the p-value will tell us whether or not the predictor The p-value will tell us whether or not the predictor is worth having in our linear model. That's what it means in basic terms. The p-value will tell us whether or not the predictor is useful in our model. Is it a tell-all, end-all story to end all stories? No. This is not the only way to select our different features. But it is one statistical way of quantifying your results. So if it's greater than 0.05, we will fail to reject the null, which doesn't necessarily mean that there is no relationship. It just means that the data that we have does not support rejecting the null hypothesis. For now, if we got 200 other markets, they might, but this data does not suggest rejecting the null hypothesis. So in stats models, to get the p-values, all you have to do is lm linear model.p-values. And you will see the intercept and the TV's coefficients p-values, which are quite small. And again, p-value being the probability that what we're looking at happened by chance, the line that we got happened by chance. If that's a really low number, that means that we are hardcore going to reject the null hypothesis in favor of there is a relationship. Note that we generally ignore the p-value for the intercept because the intercept isn't related to any of our predictors. So we don't really get a choice to reject the intercept. It's just mathematically you can create a p-value for it, but we ignore it. We only look at p-values for coefficients of our predictors. So TV seems to be very significant because it's a very low number. Low numbers are good for the predictor because it's useful. So we will believe that there is a relationship between TV and sales. Now, how well does this model actually fit? Because sure, we can use our p-values and we'll use them again down below to make our model a little bit better, but better is relative. Better is very relative. Better depends on what metric you actually want to use to measure how well your model is doing. And in regression, there are many ways of measuring how well your model is doing. And today we're going to learn a few of them. Now, in classification, we learned only one so far, only one metric for telling how good our model is doing. What is the one metric we kept using for classification? Begins with an A. Accuracy. What is accuracy? It's not a probability. It's not bias per se. It's a little bit simple. It's actually a lot simpler than that. Accuracy is just the percent of times a model is right. That's it. The accuracy is the actual percentage of how often the model was correct in predicting the category. So if there were 5 flowers and they were all setosas, if the model said setosa, setosa, virginica, virginica, versicolor, the accuracy was 2 out of 5, 40%. They only got 2 out of 5 right. That's all accuracy means, is how often was the model correct. That's harder to do in regression, period. Because correct means it was 18.5, I guessed 18.5. I hit a nail on the head, I was right. But what if you said 18.49 or 18.51? That's wrong, but I mean, it's pretty good, right? So in regression, accuracy doesn't really seem to translate over so well right away. So one of the metrics that we can use is called R-squared. R-squared is a fairly common way of evaluating overall fit of a linear model. And what it is a proportion of the variance explained. So what it means is, it's the proportion of the variance in the observed data that is explained by the model. Variance meaning how spread out it is. So an R-squared is a number between 0 and 1, between 0 and 1. If it's closer to 0, it means that the model isn't doing a very good job of predicting the variance, how spread out it is. If it's closer to 1, the model is doing better at explaining why the data is spread out in the way that it is spread out. So down here, this data, the scatter, it's pretty spread out, right? So this blue line, when it starts where my finger is, the index finger, this blue line that goes straight down has the worst R squared because it doesn't do a very good job at explaining how spread out or in the shape that the data is in. The green and the red that are curved, they do a general better job at explaining the shape, essentially the shape of the data. So R squared is a measure of how well the model is fitting to the shape of the data. If the data happens to be a line, a perfect line, and the line goes right through it, your R squared is 1. It explains perfectly the shape of the data. It's very easy to get R squared. It's lm.r squared. In general, a higher R squared is better. Closer to R, the closer to 1, the better. Now, that comes with a caveat, and also you can do it. It's 2 lines of code in scikit-learn. You do a predict, and then you do the R2 score. Then you have to give the Y and the Y predictions. But you get the same number. The threshold for a good R squared value is very dependent on the particular domain. Here's what I mean. Data takes on certain shapes in certain domains. Here's a good example. If I want to predict human behavior is generally more erratic than television budgeting and sales data. Even though that is some essence of human behavior, it's a very concentrated idea in human behavior. If you want to predict something as general as, will Sanan brush his teeth within 60 minutes of going to bed or before 60 minutes of going to bed? That's a very broad question. And it depends on so many things in my life. When my dog needs to get walked, when I ate, if I want to eat ramen right before going to bed, which happens more than I'd like it to happen. What if I want to watch Futurama? It totally depends on what I'm doing. It's a very erratic human behavior that is very hard to predict. The shape, all of the points, all of the predictors, they're spread out all over the place because anything could happen. All of a sudden, my dog could eat a thumbtack and have to go to the hospital, and I'm not going to brush my teeth before going to bed. Who knows? Now, in that case, in the case of predicting human behavior, a good R squared is generally above 0.5. A good R squared is generally above 0.5 for human behavior. Because psychologists agree that it's really freaking hard to predict human behavior. So if you got an R squared of above 0.5, that's actually significant to the psychological community. Now in sales and marketing, it's a little different. Whereas sales and marketing is a very concentrated effort to predict human behavior, a good R squared value generally is above 0.8. If you can show that you can predict human sales patterns above 0.8, that is significant enough to go to a marketing conference. So good R squared happens to be very dependent on what domain you're in. So R squared is not a good metric if you are going to be comparing models across domains. If I want to predict sales in America versus sales in Paris, I wouldn't want to use R squared to compare between the two because of the 2 different types of people and 2 different populations and 2 different types of behaviors. So R squared is a very good metric if you are comparing different models within the same domain. But if you're comparing across domains, there are other better metrics. And to talk about those other better metrics, we're going to first talk about multiple linear regression. Simple linear regression was using 1 feature, 1 response. Multiple linear regression is multiple features, multiple predictors, still 1 response. And it looks like this. It's a line y equals beta naught plus beta 1 x1 plus beta 2 x2 plus dot 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 plus beta n xn. So there's n predictors. In our case, we'll use 3. 3 predictors and 1 response sales. So sales will be equal to the intercept plus beta 1 TV coefficient times TV plus beta 2 times radio plus beta 3 times the newspaper. To do that in scikit-learn, we will create our column features, grab those 3 columns. Our y is still our sales, as always, x and y. We'll fit a linear regression, or we'll instantiate, we'll fit it in the next line, and then we'll do the same thing. We will get our intercept as 2.9, and our coefficients, which are in order of the columns that we chose, TV, radio, newspaper, our TV, 0.04, our radio, 0.18, and our newspaper, negative 0.001. Interesting. What's one thing that's weird right off the bat? Yeah? Negative coefficient at first looks weird, right? Yeah. But let's stick on that negative thing for a while. What else do you know about that number that's negative?
Very small.
It's really close to 0, isn't it? It's really small. It's really close to 0. I almost have a hunch that there might not even be a relationship at all. And we'll use p-values to see if we can figure that out a little later. That's catching our eye, so good observation. A negative number is interesting. What about between these two? Anything weird here? To you? TV? Radio? Which is bigger? Radio's way bigger. I mean, compared to TV, TV is 0.04, radio is 0.18. That's more than 4 times difference. That seems weird at first, because it looked like TV was much more correlated. We're going to keep that in mind. So here I'm just kind of zipping them together to show a list of tuples. To interpret again, and here's where we can kind of start to explain that quadruple number in the coefficient of radio. For a given amount of radio and newspaper spending, an increase of 1,000 TV budget is associated to an increase of 45.8 widgets. Remember, they're in the thousands. For a given amount of TV and newspaper spending, so if you use constant TV and newspaper, if you increase radio, it's an increase of 188 widgets. And for a given TV and radio, an increase of $1,000 in newspapers leads to a decrease of 1 widget. Why is radio so big? How can we explain that? I'm going to scroll all the way back up here, because this is why I love this data. Because no one ever calls me out on when I do this. Every single time I do it. What's wrong with this graph? The x scales are totally wrong. They're totally different. No one ever calls me out on that. The x scale from here is 0 to 350 and 0 to 60. What does that mean? They look like the same thing, but really, in terms of slope, if I increase 1 bar, so 1 horizontal bar to the TV, I'm jumping from 0 to $50,000. As opposed to here, in that same jump, I'm jumping $10,000. So it takes less money in radio to achieve the same height. So from 0 to 300,000, my sales went from 0 to 25,000. But in radio, good calls, thank you for pointing this out, when you jump from 0 to 60, it also jumped to 25,000. So because the scaling was different, we kind of overlooked at first that radio actually has a much bigger impact on a per unit spending. Because we were all drawn to that thing that we love to see, the line trending up. And that's where the data scientists have to be very careful. Because it's very easy to get stuck in, yeah, that's totally the most correlated thing, focus all of our money on TV right now. But what we just saw is, well, it actually, if you spend the same amount in radio, you get quadruple the amount of sales. So that's really important to notice. And the normal businessman who just looks at those charts would just say, yep, that line's more steep, do that. I love this data set. It's so good. Oh, God. Where am I? Here. Okay. So, my hair is going white. This is crazy talk. This is amazing. And we're all blown away. I can tell. You're literally on the edge of your seat. It's literally... So what do we do with this information? What do we do with this information? Well, when I decide to spend money on advertising, should I spend it on all three? Here's where we get into feature selection. Feature selection is how do we decide which features to include in our linear model? How can we best explain sales? Is it through all three of our variables or only two or one of our variable? One way we can do this is by looking at the p-values. If we look at the p-values of all of our coefficients, we can get an idea for which ones we should keep. So here, I will make a linear model from sales, tilde, so correlated to TV plus radio plus newspaper, given the data, and fit it. P-values. We'll ignore the intercept. TV, 1.5 times e to the negative 81. Very significant. Radio, 1.5 e to the negative 54. Less than 0.05? Absolutely significant. Newspaper, 8.5 times 10 to the negative 1, which makes our p-value what? 0.85. Is it less than 0.05? No. So with that p-value, what do we do with the null hypothesis? The null being there is no relationship. Do we fail to reject it or reject it? We fail to reject the null hypothesis. Meaning, at this point in time, we cannot say with certainty that there is a relationship between newspaper and sales. So, that leads us to believe that we can actually achieve a better model by not including newspaper. Now, to kind of put more in perspective, the TV is a lot smaller than radio, which we generally associate as being a lot more significant. But we also just saw that radio has led to a bigger increase in sales. What you are seeing the difference of in numbers is that smaller p-value is essentially another way of saying that there is a stronger correlation between the two. In radio, there's a not as strong correlation. However, the correlation itself is very powerful. It's almost like saying the TV is a very consistent measure, but you have to spend more to get there. The radio seems to be more spread out, but high risk, high reward. This is low risk, but you gotta spend more money. This is high risk, high reward. It's another way of putting it in layman's terms. Low risk, low reward, high risk, high reward. Low risk because it's higher correlated. The p-value is much smaller. The confidence interval is much tighter. But look how much you have to spend to get up to 25,000. But here you only spend 50,000. But if you spend 50,000, you might also only get 6,000 sales as opposed to 25,000 sales. You have a higher risk. It's just like it's an addiction. It's gambling. No. So p-values. So it's suggesting that newspaper we might ignore. So this approach has some drawbacks. What we just did, the p-values. Linear model has a various sort of assumptions that I had not explained up until right now. There are a lot of assumptions. One of the most important being that in a linear regression, you assume that all of your predictors are independent of each other. Or else none of this necessarily is mathematically sound. Now, a lot of the times in nature, the features are somewhat related. That doesn't mean you can't use linear regression. It just means that you have to be aware of that fact. And you have to be able to be confident to say, if we assume that all of our features are independent. Now, can you think of two features that are definitely not independent, that people at a math conference or stats conference would call you out on? If you're trying to predict sales, name two features that is very arguably related to each other. If I try to predict sales, it'd be what and what? How about? Yep. Timing and what?
Of the ad.
Timing in the ad and what? So what's the other one that would be very related to that? And viewership. Honestly, that could be, yes. Because at a conference, people would say, well, yeah, if you time it at 4 in the morning, your viewership was low. If you time it at 8 p.m., your viewership was high. So yeah, your timing is very much depending on how many people will watch your ad. And if that argument could be made, you have to think again about your linear regression. Are you doing it the right way? Now, in terms of TV, radio, and newspaper, yes, you could potentially argue that there is a relationship between radio, newspaper, and newspaper, TV ads. However, it is not out of the realm of possibility to believe that, well, however much we spend on TV, that doesn't mean we're going to spend more or less on newspaper. I mean, we see the appeal of both, but how much we spend on TV doesn't depend on how much I spend on the newspaper necessarily. You can make that argument. And if you choose to accept that argument, your math becomes more sound. So if your features are very related to each other, a linear model will start to break down. If all of your predictors are somehow related to each other, here's a very simple one. If you have two features, the year you were born and your age. You giggle because that's, yes, of course, the year you were born depends on how old you are. So if you have features that are related to each other, your linear model makes less sense. So you want to make sure that your predictors are in somewhat not so related to each other. So just be careful of that. And if those assumptions are violated, p-values are less reliable. So if you have an assumption that all your predictors are related to each other somehow, p-values mean less. That's just how it is. So if you're doing a p-value route, make sure that your features are more or less independent of one another. Using a p-value of 0.05 means that if you add 100 features, even if they're all random numbers, and I mean random noise, static, they don't mean anything. It's the number of movies Nick Cage has been in since he was born. They mean totally random numbers. If you add 100 features, if you have a cutoff of 0.05, that means on average, 5 of them will count as significant. Because if you choose a p-value of 0.05, what you're essentially choosing to do is say, out of every 100 features, only 5% of them will be significant. But that means if you add 100 features of noise, 5 of them, on average, will be considered have a p-value of less than 0.05, mathematically speaking. So these are things to be aware of. So if you have several hundred features, even if you have 300 features and 298 of them are complete random gibberish, 5% on average, 5% of those features will be considered significant based on p-value. So there are drawbacks. So if you have some fairly few number of features, generally less than 20 features, and they're all independent of one another for the most part, p-values make a lot of sense. If you have several hundred variables, I would suggest using another way of feature selection first, which we get into several times. But for now, if you have less than 20 features and they're all pretty much not related to each other, p-values are a fantastic way of feature selection. You could use R-squared for feature selection. So here I have sales related to TV and radio only. And the R-squared is 0.897, which is pretty good. 0.897,194. Here, I added in newspaper, and my R-squared went up, 0.8972106. Not by much, but it went up. So, you could argue that the increase in R-squared, which is the increase of variance explained, went up, means that your model is doing better. But here's the problem with R squared. Every model has pros and cons. Everything has pros and cons. R squared will increase 100% of the time as you add features. If you add a feature, your R squared will go up. No chance, no doubt about that. Whether it's a lot or a little, your R squared will increase for every feature you add. So why is this useful? Well, if it jumps significantly, as in a jump from 0.6 to 0.9, you can bet that that feature probably added a lot of explanation. But don't be fooled. Just because your R squared went up a little bit doesn't mean that your feature is adding more explanation. We've already deduced that newspaper seems to have pretty much zero correlation to sales with the scatter plot, with the p-value. We've pretty much already decided that. So here, R squared is tricking us. So be careful with R squared. There's another metric, which I'm not going to get into so much right now, called adjusted R squared. The adjusted R square will not go up every time you add a feature. It actually does a better job of explaining, it penalizes model complexity, but it generally under-penalizes complexity. So it makes more complex models seem like they're doing better. Again, pros and cons. And I'm aware that I'm kind of throwing at you a lot of different metrics for regression, and right now I'm showing you how they're used, and what I want us to start doing is using that Yelp data set to kind of just see how well it actually predicts data. And the reason we're doing all this in 2 dimensions is because, well, it's hard to visualize 3+ dimensions, especially on a computer. So right now we're doing it in 2 dimensions, but all of this fits for 3+ dimensions. So right now, this is a 4-dimensional feature space, right? We have TV, radio, newspaper, and sales. We have 4 dimensions going on. So our line is actually happening in 3 dimensions. So we can use p-values, R squared, and all of them have pros and cons. But personally, I think the better approach is cross-validation, the train test split, the same thing we talked about last time. I would definitely still consider p-values for feature selection. Definitely consider using R squared for feature selection. I definitely recommend using cross-validation for feature selection, using all 3. So this will attempt to directly estimate how well your model is doing and how well it generalizes to out-of-sample data. The whole point of cross-validation, where we're training on part of it and testing on the other, that whole idea, we do that because we want to estimate how well our model does out of sample. So when that 201st market comes in, we want to estimate the sales, how well will it do? It relies on fewer assumptions than in that linear regression, and it can easily apply to any other model, not just linear. It could be quadratic, it could be any kind of regression, we can use cross-validation. So here's how we're going to do it. So the evaluation metrics for classification problems, such as accuracy for classification, right, how often you're right, they're not useful for regression. So we need evaluation metrics for comparing continuous numbers. So here I have a true value, 100, 50, 30, 20, and a predicted value, 90, 50, 50, 30. Here are 3 different metrics, and I'll explain the pros and cons of each one. Mean absolute error is literally the average of the absolute value of the errors. So I'll take each prediction, subtract it from what it was supposed to be, absolute value, and then find the average of that. So it's literally the average value of error. I'm sorry, the average error. It's literally the average error. On average, how much am I off by? I'm going to explain all of them first before I get into the pros and cons. Mean squared error is, instead of taking the absolute value of the residual of the error, I'm going to square it and then find the average. So for each value, I'll take what it was supposed to be, minus the prediction, square it, add them all up, and divide by however many points there were. That's the mean squared error. Note the difference already. The mean of the same two values, the mean absolute error was 10. And the way we got that, 100 minus 10 is 10. 50 minus 50 is 0. 30 minus 50 is 20. 20 minus 10 is 10. The average of all that, of 10, 20, and 30, is 10. It's the average residual. However, when I square them and find the average, I get 150. It's a much bigger number already. Now, mean squared error is better, and I'll explain why in a second. Root mean squared error is probably the most common form of error that we use in regression. The root mean squared error, RMSE. In fact, if you choose to do a Kaggle regression contest, they will very, very likely judge you based on your root mean squared error. What your root mean squared error is, it is your mean squared error, but the square root of it. Ta-da! So for every point, you take that point, subtract it by its prediction, square it, find the average, and then square root it. So it's the square root of 150, which is 12.247. So 12.247 is the square root of 150. So comparing them, MAE, the mean average, the mean absolute error, is the easiest to understand. Subtract them, find the absolute value, and then average them. MSE, mean squared error, is more popular because I think, someone said in the front row, I think you said it, it was you, sorry. The mean squared error punishes large errors by squaring. So before, there was a difference between 30 and 50, which is 20. And a mean absolute error, the error was 20. But when you square it, what does it become? 400. So when you square that distance, when you square the residual, you are punishing larger gaps in the prediction. Root mean squared error is the most popular. Root mean squared error, where'd you go? Because it's more interpretable in Y units. 150, there's no really units to 150. But 12.24, you can definitely have a meaning to that. 12.4, on average, we can expect to be off by 12.24 in the thousands, so 12,000. So here's an additional example. So 100, 50, 30, 20, 60, 50, 30, 20. All of them are the same except for the first one. The first one's off by 40. The mean absolute error is still 10. The root mean squared error is 20. It's 20 because it highly punished the distance between 60 and 100. Generally, root mean squared error is better in the real world. Generally. And most regression problems will ask you to judge your answer in root mean squared error, if not other metrics as well. But definitely root mean squared error. So, how do we do this? And this is the last thing I'll do before I kind of turn to the yup data set and explain it a little bit, and then get into what I want to do for next class. Here's a function I wrote. What it does is, it takes in your x and your y. It will do a train test split. X train, X test, Y train, Y test. Which does what again? It splits it up into, what does it do? What are those four numbers, or four variables? What is X train?
Training data and testing.
Training and testing. So, Desiree, you want to say a little more? What is X train specifically?
So, X train is all of the set of training data that you will use that correspond to the independent variables.
Right, it's the predictors that I'm going to use for my training data. X test is my training response. My Y train, Y test, I will fit my data to my training and then score it on my test. That's my cross-validate. That's my my train test split. So I'm going to fit my linear regression to the training data, I'm going to predict the test data, and then I'm going to give you the root mean squared error of my predictions and my actual responses. And when I do that, for TV, radio, and newspaper, I get a root mean squared error of 1.404, which is not coincidentally the square root of 2. Yes, it is. 1.404 is the square root of 2. Now, if I exclude newspaper, which we kind of all agree that it's probably a good idea because it doesn't seem to be helping much, my root mean squared error goes down, which is good. So the root mean squared error, to explain like to a board of directors, all right, if we use TV and radio sales to try to predict, or TV and radio budget to try to predict sales, we will, on average, be wrong by 1,380 units. That's how you interpret the root mean squared error. It's pretty much you say how, on average, I will be wrong by 1,380 units, as opposed to 1,400 units up here. So your general goal is to reduce your root mean squared error as much as possible. You want to have your r squared as close to 1, your root mean squared error is close to 0, and you use your p-values to select your features. Now, last thing I'll talk about linear regression. So here are the general advantages of linear regression. It's easy to explain. As for every $1,000 of budget in TV, we will sell 48 more widgets. Done. That is a very simple sentence to say. Our 95% confidence interval suggests that the actual coefficient is between 0.045 and 0.55. 0.055. Done. Very simple sentence to say. Using our p-values, we are able to deduce that newspaper does not have any distinct correlation to sales, whereas TV and radio does. Radio appears to have a quadruple the amount of return than TV does. Very simple sentence to say. As we spend $1,000 in radio, we get 188 widgets sold. As we spend $1,000 in TV, we only sell 48. That's a very clear difference to the salespeople. 4 times as many. It's very simple to explain the numbers behind it. It's very easy to interpret. The metrics are very easy to interpret. If I have a root mean squared error of 1.2, that means on average, my prediction will be wrong by 1,200 units, on average. It's not good necessarily, but it's very easy to explain to someone what that means. On average, I'm wrong by 1,200 units. It could be 10,000, but it's 1,200. Model training and prediction are very fast. To fit a line of best fit, it's very quick. It's actually a one simple linear algebra equation that is done in the back end. Again, if you're interested, we can show you that equation. No tuning is required, except if you really want to do a very advanced linear regression called regularization, which you can look up on your own, or we might do later on in class. But for the most part, there's no grid search. There's no, okay, try this metric. Okay, try this metric. Okay, try this metric. No, it's just, you have a line of best fit. You use p-values to select which features you want, but that's it. There's no, you don't tune, I want this k, or I want this many degrees. No, it's set. You have 1 degree, you're a linear regression. You don't get to do a curve. So there's no tuning parameters. Features don't need scaling. As long as you know how to interpret your model, you don't need to scale anything. You don't necessarily need to normalize your data. It doesn't matter that TV and radio were on different scales, as long as we can recognize and deal with it. It doesn't matter that they're scaled differently. If TV is scaled to the 1, remember we scaled TV by multiplying it by 1,000, didn't change anything. The numbers were different, but as long as we adjusted our interpretation, nothing changed. So we just have to be aware of the scaling, but it doesn't matter what the scaling is. And it can perform very well for a small number of observations. That's probably one of the biggest pros, is that if you want to do a regression and you only have 200 points, a linear regression is a very good option for you. Very good option. Because it trains very well with a few numbers. Be aware of the bias variance trade-off here. So is it a low or high bias? Linear models. Low or high bias. This is your practice. Low or high bias. High bias, which means what? Is it good at predicting or bad at predicting generally? Bad. Low or high variance? Low variance, which means the model is consistent or inconsistent? Consistent. Consistent model, not always the best results. As opposed to other models later on, such as random forest. Random forest is very inconsistent, but high risk, high reward. Is very low bias. It's very good at predicting your values. So throughout the class, we will be exploring models on very different ends of the spectrum of bias and variance and seeing how well they can perform on simple and complex tasks. All right. So now we'll take a break and we'll get into the next 3 hours when we come back. So that's linear regression in a nutshell. It does involve a fair amount of math and statistics. I didn't get into all the formulas that go into it, but again, it is important to understand and appreciate the math behind it. And if you don't want to understand the nitty-gritty of all the equations, you want to do everything by hand. As long as you understand what R squared generally means, as long as you can interpret the root mean squared error, as long as you can effectively explain to someone what it means to be a confidence interval, or what it means to have a correlation of 0 or -1 or 1, or what scaling means. As long as you can easily talk to someone about that by the end of the course, that will be enough for you guys to actually start applying linear regression to your projects and to other things as well. So for homework, I included a Yelp data set. So Kaggle had a competition for a Yelp data set. What this is 10,000 different Yelp reviews with the business ID. They don't tell you the business. The date it was made, the review unique ID, how many stars the rating got, the actual text. My wife took me here on my birthday and it was excellent. The type, it was a review. They're all reviews, I believe. The user ID, whoever said it. How cool it was, how cool they rated it, how useful it was rated, and how funny the rating was. So the challenge, and I'll show you I wrote it out here, optional questions. So some of the questions are generally relating to, can you try to predict the number of stars given to the rating, or given to the restaurant? Given to the rating, based on the other predictors, how useful, how funny, and all that. So I kind of give you, kind of goes through it, read the Yelp data set, explore the relationship, define cool, useful, and funny as the features, and stars as the response, fit a linear regression, evaluate the model by doing the training and testing. Does a root mean squared error make intuitive sense to you? So find your root mean squared error. Can you, in a sentence, explain what that number is? There's some bonus ones. Think of adding new features. So for example, you have the whole body of the text. So for example, if you want to count the number of times the user says excellent, or good, or amazing, or crappy, terrible, things like that. If you want to count the number of negative and positive words that can get feature that you add to the data set. To see if you can add a feature to see if that helps you predict the number of stars that they're going to give that rating. And yeah, so just a couple of questions to kind of get you started with linear regression. This is optional, totally optional homework, but I will tell you that your next mandatory learning opportunity will include the Yelp data set. So I will be asking you to use the Yelp data set in your next homework assignment. So it's a good idea to start working with it now to at least get an understanding. And so if you try to open it in Excel, it's super slow. I'm trying to resize the column E with the text, and it's already about to crash on me, and it's only 10,000 rows of data. So this is a really good chance to see how Python is a lot quicker way of just manipulating data, because it's still thinking about how it's going to resize that column for only 10,000 rows. All right, are there any questions about anything we've done today, linear regression? So as of now, we have seen an example of classification and one on regression. On Wednesday, we will be, on Wednesday, we'll be looking at a new model called logistic regression. Do not be fooled by the name. Logistic regression is actually a classification algorithm, but it does something very interesting. It turns a classification into a almost type of regression. by turning a true or false question into a question of predictions or probabilities between 0 and 1. So to prepare, if you feel like your probability is not up to par, I included several videos and articles about how to do some basic probability stuff. So up here, probabilities and odds, intuitive guide to exponential functions, and the natural logarithm. Those are especially important. Under the resources are just more linear regression resources. So this homework is reading to help you with Wednesday's class because I'll be talking about probability, what odds are. They're not probabilities, they're different things. What odds are, and some E, the natural logarithm, and so those are definitely very helpful. And these are just all on. So the lesson today was adapted from the Introduction to Statistical Learning, which is a fantastic book. It's totally free. They give it away for free. Chapter 3 is all about linear regression, and that's where this code was actually adapted from. This book actually uses the same exact data that I use, so, well, I took it from them, so that's why. They use the same data, so they'll actually explain it with using the same data, so you can have a better, they'll explain it another way. Yeah, are there any questions? If you, by beginning of Wednesday, if you still don't have a review on your homework or your project, please tell us immediately in the beginning of Wednesday's class. You should have it by Wednesday. If not, have a great night, guys. I will see you in 2 days.